Hi everyone, so this will be our last video series for Chapter 10, and so this will cover the last two sections of Chapter 10. And so we're going to start with reactions of acids and bases. So I've alluded to in a couple of other videos that acid-base reactions are quite common in biology and in medicine, and so this will be a particular focus for us. So, reactions with acids. So we're going to look at three different types of reactions. So we've actually, now by the end of getting to Chapter 10, we've actually racked up a good amount of types of reactions that we're familiar with. If you need a refresher, I'd say go back, what is it, Chapter 6, I believe? Or maybe it was 7. It has the different types of reactions. So that is something we did before spring break. So use some of the practice problems or office hours if you need a little bit of help. So the ones that we're going to look at are going to be metals to produce salt and hydrogen gas, so the acid would be reacting with metal. Acids that react with bases to produce salt and water, and water. I think most people are familiar with this particular reaction. It's usually the high school definition of an acid-base reaction. And then we'll talk about bicarbonates and carbonates that are going to react with acids to produce carbon dioxide. And even though you may not be familiar with the way it's worded, you've actually probably done it when you were a kid. That's exactly what happens when you mix together vinegar, which is acetic acid, and baking soda, which is sodium bicarbonate. And so we're producing CO2, like the bubbles that you'd see in kind of like a middle school volcano project. All right. So let's go through those one by one. The first is going to be acids and metals. Right? So acids don't react with all metals, so I'll have to tell you if they're going to or not, but here's just some representative metals that do react with acid. And so what I have down at the bottom are just two examples of using potassium and then also zinc. So in both examples, again, I'm going to use that strong acid, which is HCl, hydrochloric acid. We know it's going to be strong because I told you. And just to remind ourselves what the definition is of strong, it's saying that when it's dissolved in water, it's basically going 100% into H plus and Cl minus. And actually, to be even more sophisticated, let's be correct all around instead of using shorthand. Let's write out the whole balanced chemical reaction. Water is going to be reacting with that hydrochloric acid. And it'll go to basically 100% completion. 1H gets donated to the water, which will accept it. So we have our Bronsted-Lowry acid and our Bronsted-Lowry base. So we end up with hydronium and chloride. That's more just a review of the other sections that we did. So let's get back to what we were doing. We have our strong acid, HCl, reacting with potassium. And so this is just potassium metal. And so what we see here is it ends up being a single replacement. Well, not quite single replacement, actually, I shouldn't say that. But if we look at the balanced chemical reaction, what we're going to do is recognize, okay, it's an acid and a metal, and we're going to say, okay, it's producing hydrogen gas and then a salt of the metal. So hydrogen gas has to be a product, and the way we figure out the salt of a metal is you'll take the metal cation and then the acid's anion, whatever that happens to be. So I don't know if we've actually explicitly defined what a salt is. So salt is not just table salt. It's a generic term. It means it's a compound that has been produced by an acid reacting with a metal. So it's going to form a salt. So if you're talking about like sodium chloride, which is table salt, that's like taking sodium, adding it to hydrochloric acid, and we'll have to balance it, because we know it's going to make H2 gas, so that's balanced, and then I'm left with 2 NaCl. And that's what you eat. That's table salt. If you eat sodium, your mouth would explode, literally. All right, and then we can see the same thing with zinc, right? There's my metal. There's the counter anion of the acid, so my salt is zinc chloride, right? The only difference is zinc is found in group 2, while potassium is found in group 1. We know all group 1 have +1 charges. All group 2 metals will form 2+ cations, so we've got to make sure everything balances correctly. But we see the similar pattern. We formed our salt, and then we formed our hydrogen gas. So what you would see in this particular reaction, and sometimes HCl can be extremely vigorous, we'll say, when it reacts. So occasionally you can light the hydrogen on fire. But if this was done gently, you'd see bubbling because it's producing gas. So now let's talk about acids with carbonates and bicarbonates. So this is, I only had you memorize one of these polyatomic ions, so that's all I'm going to have you deal with, I guess, in the sense for this chapter, because that's the polyatomic ion that I chose. But just keep in mind that's going to work for things such as bicarbonate, and if we look here, the only difference really is a hydrogen is part of that polyatomic ion down here, so the charge is going to be one less. Carbonate is a 2-, and then bicarbonate is a 1-. So we take a look at what happens when the two react. Actually, let me just wipe everything. There's my acid. Make sure it's balanced. There is a carbonate. Doesn't matter what it is. So we're going to see it forms carbon dioxide. The salt of whatever the metal is, in this case calcium, with the anion of the acid. So there's my calcium 2+ with the anion of the acid. And then a third product, which is going to be water. So for us, gas, salt, and water is what we'll need to be familiar with for this particular type of reaction. Oh, getting a delay here. Yeah, almost. Here we go. There's a delay on my iPad is what it was. And then the last reaction that we'll take a look at is going to be neutralization reactions, which I think most people are familiar with because this is usually the high school reaction that you deal with acids and bases. So we only produce two products, the salt. Again, when we're looking at salts, it's going to be the cation from whatever's doing the reacting, from the anion from the acid, so NaCl. The difference here is now we're reacting it with a base, and it's not just a pure metal, right? One of the examples I showed you was sodium reacting with hydrochloric acid, right? And that was different than this because even though sodium's in it, right, sodium hydroxide is an ionic compound. It's not a metal. Oops, wrong thing. That's what I wanted to do. So, I don't know if there's much more to say than that. We've seen salt formation now twice, so same idea. It's just recognizing there's an acid and a base, and then I'd have to tell you that information. So if it's like an exam or something like that. So how do you tell if you're going to balance particular chemical reactions? So when you're dealing with neutralization reactions, and this is why always one of the products is going to be water, is that the H+ from the acid is always going to react with one OH from the base, provided by the base. So what we see down here is if we had, so this is explicitly written out, so what we have here, if I was going to write it in short, in the molecular, sorry, tripping over my words, the molecular equation, which means nothing is drawn as separated like this. So if we took our HCl and the NaOH, sorry, this is people texting me, right, and then we'd have our salt and water, right? What we can do is take, I'm going to mute that, is recognize acidic plus sodium hydroxide only had, and then whatever's left over, right? All this is the net being net profit that's after, and you've taken in all of your, so things kind of cancel out. What we see here, it appear on both, and what do I mean by that? Hand side of the ring here, underline, I got a, it's a little bit weird here on the products, Na+ and Cl. They exist, but and that's why the net ionic, the important bits going on. Important bits here on both sides, the later color. Right, reactant side, I have over here on the product side, there's no hydrogen, there's a water here, and stick around, and the ionic equation. So why do we care about acid-base reactions? Well, they're important in biology, and we're going to get to them eventually when we start talking about enzymes and proteins. But as a chemist, and actually as a nurse, you'll do this too if you've ever heard of titering your blood. This is what we're going to talk about. So a titration, oops, at least it's a gross color. Let me change back to highlighter. Right, a titration is just going to be a laboratory procedure to determine the molarity of something. In this case, it's an acid-base reaction. So it's usually of the acid. Doesn't have to be, you could flip it around. But in our case, we're just looking at acid being titrated with a base. So you have a known concentration of NaOH, and you can neutralize an unknown. This goes back to 1 when we started talking. Phthalate is a color from clear. Just as it gets to around that, so for that neutral Ch7. So it's usually just kind of like an approximation of getting close. And as it just turns a little bit pink, that's really indicative of being close to pH 7. So how is this done? Usually it's done in a burette. And so that means we have a very finely calibrated or finely gradated instrument. Gradations meaning just lines on it, right? So it's easy to determine how much of a base, in this case, that you're adding or titrating. It's a little bit finer than a graduated cylinder, which usually goes to 1/10 of a mil. These usually go to 1/100th of a milliliter. And then what you do is you'd turn the stopcock and then add slowly dropwise the base to the acid solution until you see it change from clear to pink. At that point, you would know the titration is done and that the concentration of the base, or actually I shouldn't say the concentration, I'd say the amount, is the moles of acid. That's what makes it powerful. Because if I know one, then I know the other. And so this is what I was talking about in an indicator dye. So certain chemicals, depending on if they react, is an acidic solution or a basic solution, will change color. And so with phenolphthalein, that's what you're seeing here, that pink color I was talking about. In the last picture, it was clear. Now you can see it's starting to turn to pink. So at the end point of the titration, and this is what a couple of slides ago I said, the moles of base, forgot if I don't turn on the tool, it just skips ahead. The moles of base are equal to the moles of acid in solution. So if the concentration of the base is known, which would be the one in the burette, so I know that, and if I know the volume of the base used to reach the end point, that means I would know amount of base, and then I would also know the volume of the base in liters, so that's going to be concentration. Wrong tool. So what we can do then is say the molarity of the acid is calculated using the neutralization equation for the reaction. So I know exactly how many moles of base I titrated, right? So by doing some stoichiometry, I don't think, have we used that word before? I usually call it dimensional analysis. Same thing. And we can figure out from this known amount how much was originally in that acid sample. All right, so the very last thing we're going to talk about are buffers. These are really important, especially in nursing. So if your blood, humans only pretty much operate at a very narrow pH, even though all over your body it's different pHs. Like your stomach is around pH 1. At one point in your intestines, it gets to like pH 10 or 12. It's very, very basic. But your blood is, I believe, around, 7.2 to 7.4, right? And what ends up happening is usually when you eat or you breathe, you can change the pH in your body, and you want a system that's going to resist those changes. The reason for that is because humans, or any life, if you get outside that narrow operating pH, it very quickly leads to death. So, what is a buffered solution? Right now, our definition is it's a solution that when you make it, the pH is maintained. So what I have here is just a pH, just water, and it's pure water because of a pH of 7. I can either add more hydronium, which could be like maybe adding a small little bit of like acetic of hydrochloric acid, and we see the pH immediately and precipitously drops to 4. I could do this similar experiment instead of I could just add sodium hydroxide to the water, and immediately and very quickly the pH will drop to 10.5. So in both cases, if your blood did that, you'd be very quick. However, which we're already and we'll explain exactly, but if you have a buffer, add a little bit of acid, go down a little bit, but add a little bit of hydrogen, almost maintain 7. Let's explain why that actually happens and what makes up a buffer. So why do buffers work? So we already defined them as resisting changes in pH from the addition of acid or base. So in humans and in animals, we're going to absorb either hydronium or hydroxide, depending on what you eat, from certain foods, mostly cellular processes. A lot of them will generate protons, which are H+, which will then react with water to make it acidic. So you need a process to keep the pH around 7.4. In your blood, actually, you have a carbonate buffer where it goes between the carbon dioxide you breathe and making carbonate. And it actually acts as a buffer, but that's a little bit beyond this course. But actually, it's the CO2, after you've inhaled, oxygen, and you've respirated, that CO2 is actually used to, part of it is used to keep your blood pH at 7.4. All right. So what is a buffered solution, right? We've defined it as saying it resists changes in pH, but what exactly is it? So it's going to be a combination. It's going to be a mixture of acid and bases, and we're going to call these conjugate pairs. So conjugate means that they're together, right? They behave together. So it means you're going to have something like a weak acid. In this case, I have acetic acid. Or actually, because I'm looking at, is that acetate? I'm not going to commit to naming it right now because it's written in a weird way that I'm not used to, with like the way it's written. So I'm just going to call it generic weak acid for now. Sorry about that. But what we see here is if we remove this H, well, then if I was talking about neutralization reactions, right, that would be that anion of the acid. Because they look almost identical, we're going to pair, because the only H to make it the N, plus the H to make it the. So when you have, that's actually, so we'll get into the shadowing, right? Because if you have the acid, so if we have a good amount of weak acid around, and then I add some base, I have a good amount of the conjugate base around. Our buffer right here will then react with the little bit of acid, enough conjugate base to go and neutralize that acid. Kind of as a tug of adding a small amount of base or acid sucked up, but limits that change in pH. Oh, so it was acetic acid. Good, that's what I thought it was, but I couldn't tell the way it was written. All right, so this is kind of what I just sketched on the last page, but shown as a figure, right? So there's my acetic acid and an acetate ion. So this is where we're starting over here. So there's my weak acid and its conjugate base. I add a small amount of OH, and what's going to do is that OH interacts with that little bit of acetic acids that there, converts it to acetate. So yeah, the acetate concentration did go up, but only by a little bit, and it's weak. And so we still got a good amount of weak acid around. The buffer is holding. So this would be a buffered solution. So it changed the pH a little bit, right? But it was able to compensate instead of having a massive shift to a high pH. And then the same thing on this slide as well. There's my buffered system that I had before, but instead this time I'm adding acid. So if I'm starting, it's a little bit weird, I'm starting from the right-hand side of the screen, but there's that equal amounts of acid in its conjugate base, add a little bit of hydronium. Some of that hydronium is then sucked up by the acetate, so the concentration goes down a little, but it makes a little bit of weak acid, so it's really keeping that pH close to where you started. All right, so that's going to end our slides for all of Chapter 10. So it ended up being longer than I would hoped. But what my plan is for Friday, so tomorrow, which is going to be March 27th, I believe, just to keep, because I know I say tomorrow, but you guys could watch this later. So yeah, March 27th. What we'll spend all of class doing is I've already sent out practice problems. So those are for Chapter 6 through 10. If you want to focus on things from 10, I'm more than happy to do that too. So if you can just, well, actually, if you got to this point, you probably watched all the videos, but I'd say if you've done that, by Friday, by the time we meet, I think you're in good shape. All right, I'll see you on Friday.